Okay, hope everyone is here and all right. Okay, so if you have any questions, just unmute yourself and speak up. I'll try to pay attention to the chat too, but it's a little bit more it's easier if you just speak up. Okay. And if you can, please turn on the video so that others know that you are also here and we can make it more interactive. Otherwise, it's also fine. Okay. So, all right. So last class, we were talking about the low rank approximation problem. Okay. And then we talked about the singular value decomposition. And today we'll see how SVD connects to principal component analysis and low rank approximation. And then we'll talk about a very important algorithm called the power iteration. Okay. And just as a reminder, the first announcement is that, just a reminder that assignment 2 is due today at 10 p.m. Okay, so just keep that in mind. And, instructor office hours will be remote as well. Okay. All right. Okay, let's take a quick look at where we were in the last lecture. Right, so last lecture we just defined what singular value decomposition is, and then we saw a couple of examples of what singular value decompositions can look like. Right, and today we're going to continue the discussion by first stating two magical properties of SVD. So there are two magical properties of okay, so two magical properties of singular value decomposition. All right, so these are magical in the sense that there's no they make certain problems much easier to solve, even though they are highly non-convex, and typically they should be very difficult to solve computationally. Okay. All right. So what are these magical properties? Let's just review what singular value decomposition was. You had a matrix X. We said we can write it as U times sigma times V transpose, right? So if this was a n by D matrix, then this would be an n by R matrix where R is the rank, and this is an R by D. Okay. And so typically the singular values, all we know is that they are the matrix is a diagonal matrix with non-negative entries on the diagonal. But by convention, it's nicer to order them. Okay, so we're going to write down the entries of the middle matrix in this decreasing order from the top left to the bottom right. And we can do this without loss of generality by just moving around the rows and columns in U and V. So you don't lose anything by making this assumption. Okay. And under this assumption, you have these very nice properties. So let's say you look at the rows of this V transpose matrix. Remember, we said that the columns of U are orthonormal. So they have unit norm 1, they have length 1, and they're perpendicular to each other. And same for the columns of V, right? And the main theorem that we are going to use is the following. So V1, which is the first row of the V matrix in first column in the V matrix, or the first row in V transpose, E is actually the first principal vector of X. Okay. So remember, the way we define the principal component, it had nothing to do with singular value decomposition or anything like that. But it turns out that if you can compute the singular value decomposition, you order the entries in the singular matrix sigma in decreasing order, then the first column of V will actually be the first principal component. Again, V2 will be the second principal component. And so on. Okay, so V3, the third column of a V or the third row of V transpose will be the third principal component and so on. Okay. You can tell that I'm on campus. All right. And so that's the connection between the singular value decomposition matrix and singular value decomposition and principal component analysis, right? And the next thing is that not only does SVD solve the PCA problem, it also solves the low rank approximation problem. Okay, so what do I mean? So remember the low rank approximation problem, we are given a matrix X and a number K, and we have to compute the best low rank approximation to X, best rank K approximation, right? And this is called the Eckart-Young and Mirsky theorem. This is from 1936. Okay. And what they showed is that imagine you have your singular value decomposition, you order the entries in decreasing order and form the matrix, which I'll call XK, as just take the first K columns of U. Okay, instead of taking all of the columns of U, I'm only taking the first K. And do the same thing for sigma. So I only take sigma 1, 1, sigma 2, 2, all the way up to sigma kk, right? And then the same thing for V. So in some sense, I'm just truncating the singular value decomposition to the k largest entries in our matrix sigma. Okay, then this matrix is a solution, actually is the best rank k. Okay, so if you can compute the singular value decomposition, then you can solve the best low rank approximation problem. And any questions about these two theorems, statements? Okay, so SVD solves principal component analysis and low rank approximation. Okay, it can solve both in one shot. All right. So we won't go into too much detail about how these theorems are proved. The first one isn't too complicated, but the second one is a little bit more involved. And we will skip them for this course. But if you'd like to know more about how they are proved, you can reach out to me later. Okay. So that means that if we can compute the singular value decomposition, then we can find the principal components and solve low rank approximation. Okay. So going back, just as an example, for the Netflix challenge, we said that you had to compute the best rank 30 approximation to this huge matrix, right? So we had to compute the best rank 30 approximation to this very big movies by users matrix. And we can do so just by using a singular value decomposition. So we can do it if we can compute singular value decomposition. Okay. So for the remainder of today's lecture and a little bit of the next, I want to say a few words about how do we compute the singular value decomposition. Okay. And when we think of singular value decomposition, one thing to keep in mind is that often, at least for data science applications, we don't really want to compute the full singular value decomposition, but maybe I just need to compute the first principal component, or maybe the first 10 principal components. So in that case, what I want is not to compute the full singular value decomposition. Obviously, if I can compute the full singular value decomposition, I can compute the first 10 components too. But maybe computing the first 10 is much easier, right? It could potentially be much easier. And as we will see, that is indeed the case, and we will exploit that. Okay. So before describing the algorithm for computing the singular value decomposition, which is one of the most important algorithms in numerical linear algebra, let us investigate some properties of singular value decomposition. Okay. By properties, I just mean let's write down some sort of equations and see what the SVD actually gives us. Okay. So we have a matrix X, and we wrote it as U sigma V transpose, right? And remember, we are ordering the entries of sigma as sigma 1 is at least sigma 2, all the way up to sigma R up. Okay. And so let me rewrite this equation in a couple of different ways. So the first column here is U1, the second column is U2, all the way up to UR, right? And then we have our diagonal matrix sigma and V transpose. Okay. Okay, so one question. So if I multiply out these matrices, the way matrix multiplication works, my claim is that the first column of U, what does that get multiplied with? What other entries do the first column, do the entries in the first column interact with in this matrix product? Do the entries in U1 ever get multiplied with entries in these rows? What do you think? Well, actually not, because our middle matrix sigma is diagonal. Okay. As a result, the first column only gets multiplied with the first entry in sigma and the first row in V transpose. Okay. And similarly, the second column in U only interacts with the second column in V, and so on. Okay, so let me just maybe a couple other things here. Okay, so formally, I can write this whole thing as sigma 1 times U1 V1 transpose plus sigma 2 times U2 V2 transpose, and so on. Okay. So for brevity, I'm going to write down, this sigma, the first entry in this diagonal matrix, as just little sigma 1, this as little sigma 2, and so on. Okay. So what does this mean? So we have X is sigma 1 times U1 times V1 transpose. Okay. And then sigma 2 times U2 times V2 transpose, plus so on up to sigma R times UR times VR transpose. Okay, this is just expanding out this U sigma V transpose. Given the fact that sigma is diagonal, you get this nice sort of representation. Okay, and we already said that this is the first principal vector, right? And U is called the first left singular vector. So U1 is called the first left singular vector, and sigma 1 is called the first singular value. First just means that it is the largest entry in the diagonal matrix sigma, and first left singular vector just means that it corresponds to the largest entry sigma 1. Okay, and so on and so forth. So U2 will be called the second left singular vector, right? And sigma 2 will be the second singular value, and so on. Okay. So this is property 1, that, given X is due sigma V transpose, we can actually also write it equivalently in the sigma 1 times U1 times V1 transpose plus sigma 2 times U2 times V2 transpose plus so on. Okay, any questions about this? All right, if there are no questions, then the second part is going to be the following. So given X, there's actually some sort of redundancy among the different sort of left singular vectors and the right singular vectors. In particular, you have the following equation. Okay, so if I multiply the matrix X with the ith right singular vector V, you get a scalar multiple of the ith left singular vector Ui. And the scalar multiple is exactly the ith singular value, right? Some sense, if you know Vi, then you can kind of get Ui and sigma I from that. So why is this true? Well, let's just do the arithmetic, right? So we said X, I can write it as right? So let me just multiply it this way. Okay, so far so good. This is just an equality. And now I can break up the sum times product as sum of products, right? I can write this as sigma 1 times U1 times V1 transpose Vi plus sigma 2 times U2 times V2 transpose Vi plus so on. Now, in between, there'll be sigma I, Ui, Vi transpose Vi plus so on. Okay, I'm using associativity here to group things a little differently, right? So, whether I group it like this or this times this, the answer should be the same. Okay. Now, what can you tell me about V1 transpose Vi? If I is not equal to 1, what should V1 transpose Vi be? 0. Exactly, right? Because remember, V1 transpose Vi equals 0 if I is not equal to 1, right? The columns of V were orthonormal, so they're perpendicular to each other. So every one of these will disappear except this I times I term, right? And Vi transpose Vi is actually 1 because Vi has unit norm. Okay, so this becomes sigma I times Ui. So recall columns of V are vector normal. So whenever you have two different indices, Vj and Vi, if you take their inner product, you're going to get 0. And if they're the same, you get 1. Okay. And similarly, you kind of have a analogous result for the other side. If I do Ui transpose times X, you get sigma I times Vi transpose. And the proof of this is same as above. You just have to multiply from the left, but everything else stays the same. Okay. All right. So if you know Vi, then I can at least infer what sigma I times Ui is, right? But my claim is not only can you infer what sigma I times Ui is, but you can also figure out what the singular value sigma I is. Any suggestions on how I can do that? If I know V, I want to claim we can also get sigma I from it. Well, we just saw that x times Vi is sigma I times Ui, right? So what is the norm of Ui? It's 1. Ui is an orthonormal vector, so it has length 1. So this means that sigma I is the norm of x times Vi. Okay. As okay. So given just Vi, I can get sigma I, and then I can get Ui as all right. Okay. So just to summarize, if we can compute okay, to summarize, even though it seems like in singular value decomposition, there are 3 unknowns. There's U that you don't know, there's sigma U that you don't know, and there's V that you don't know. But because of these relations between them, if you can compute one of them, let's say I can compute V1 through VR, then I can compute sigma 1 through sigma R just by using equation 4. And from there, I can compute equation U1 through UR by using equation 5. Okay. So if you want to compute the singular value decomposition, it would suffice to just focus on trying to figure out what the V's will be. Okay. All right. So how can you compute the singular value decomposition? First, there are many algorithms. It's a very important primitive in numerical linear algebra, especially in many applied sciences. It's used a lot. So there's been a lot of work on it. And pretty much any numerical software has a very good implementation of the singular value decomposition. Okay. And there is this classical result. Let me just state it. So we can compute full singular value decomposition in time that is of n times d squared. Okay. In general, if I want to compute the singular value decomposition of a matrix, I can compute all of the singular vectors, all of the singular values in time, which is n times d squared. All right. But let's get a sense of these numbers, right? So for the Netflix challenge, for example, I said that you can get an almost 4% improvement over the baseline just by computing the singular value decomposition. But to do that, n was something like 500K, and d was something like 17K, right? So n times d itself is 8 GB of memory. So I cannot use this full singular value decomposition algorithm. It's will be way too expensive. Even just storing the representation would be 8 GB memory. And then on top of that, I would run 17K times more slower, right? So it'll be very, very slow to compute the full singular value decomposition. Okay. But as I said, we don't need to compute the full singular value decomposition for the problem. All I need to do is to compute the top few singular vectors, right? Can I compute the top 30? Can I compute the top 10? And can I do this in time, which is much better than n times d squared? That's the question that we want to ask, okay? And so let's formalize it. Question. Is computing the first 30 singular vectors easier than computing the whole 17,000 of them? Okay. And the answer is yes. And this goes back to the main algorithmic tool that we'll study, which is the power iteration. Okay. And the punchline here is that we can compute the first singular vector, or first few much faster than computing all. Okay, so you can compute the first singular vector without figuring out what the others will be. And once you can compute the first singular vector, you can use some greedy strategies to extract the other singular vectors out. Okay, so how do you do that? The idea is to use some of the equations that we already saw. So remember, we said in the singular value decomposition, we can write x as u sigma v transpose. And this would mean I have sigma 1 times u1 times v1 transpose plus sigma 2 times u2 times v2 transpose plus so on. Okay. And the first step here is to, in some sense, get rid of the u's in this representation. Because, as I said, we are only interested in computing the first. If we can compute the v's, then we can get the others from v's anyway, right? So let's focus on getting the v's. Okay, to this end, let's form this matrix Y, which is X transpose times X. Okay, so what is X transpose times X? Well, it should be, you take U sigma V transpose and the transpose of that. So I get V times sigma times U transpose times U times sigma times V transpose. Okay. I can write this again as V times sigma times. Let me regroup these matrices. I'm opening up the parentheses and just rewriting some of them. Now, what is U transpose U? My claim is U transpose U is a very simple matrix. What is U transpose U going to be? It's exactly the identity matrix, right? So remember, U has orthonormal columns, right? So that means that the columns of U are perpendicular to each other and have length 1, right? So if I look at U transpose U, okay, so you have this column times this column, that would be 1. And the other inner products would be 0 because the columns are perpendicular to each other, right? So this would just be the identity matrix. Okay, so that means that Y equals V times sigma times identity times sigma times V transpose. So which is just V times sigma squared times V transpose. Okay. Now, what is sigma squared? Sigma is a diagonal matrix, right? So let me just write this down. That shouldn't be a trapezoid. Okay, so this is V. What is sigma squared? So sigma is a diagonal matrix, right? So when you take the square of a diagonal matrix, what happens? Just the entries get squared, nothing else changes, right? So I would get sigma 1 squared here, sigma 2 squared here, sigma r squared, and then I have 0 and 0. Okay? And then I have V transpose. Okay? So, all right. So this means that if I use the same trick that I used before, I can break up this matrix into simpler matrices. Okay. All right. So how do I break it up into simpler matrices? I can do the following. Right. Just as before, the first column only interacts with the first row in the transpose. Right? So I get this is sigma 1 squared times V1 times V1 transpose plus sigma 2 squared times V2 times V2 transpose plus so on. Okay. So let me write that down. So we have that Y equals this much. All right, any questions? Okay, where am I going with this, right? So the point is that we did this for y equals xx transpose, right? Now let's do just one more calculation, which is what is y squared going to be? Okay. Well, if I want to y squared, I need to compute y times y, which is v times sigma squared times v transpose times v times sigma squared times v transpose. Okay. I can move and match these things once again. What is v transpose v? In singular value decomposition, the columns of v are orthonormal to each other, right? So just as before, when we argue that u transpose u is the identity, by the same logic, v transpose v would also be the identity. Okay, so I get v times sigma squared times identity times sigma squared times v transpose. Okay, which is v times sigma to the power 4 times v transpose. Okay, and by the same logic, I would get v squared, y squared is sigma 1 to the power 4 times v1 transpose plus sigma to the power 4 times v2 transpose plus so on. All right. And okay, let's play around with this pattern. What would y cubed be? Any guesses what I'll get if I do y cubed? Well, I can do the same thing again, right? So I have v times sigma to the power 4 times v transpose, and then v times sigma squared times v transpose. Group the inner things together. Right, now this becomes identity. Okay. So y cubed is v times sigma to the 6 times v transpose. So in general, I hope you identify the pattern here. You can show that y to the power L is just v times sigma to the power 2L times v transpose. Okay. And remember, y is just xx transpose. Sorry, it's x transpose x. Okay. And to kind of, write it more clearly, I have v1, v2 to vr. So this matrix will just have sigma 1 to the 2L, sigma 2 to the 2L, sigma r to the 2L, and then zeros on the off diagonals, right? And then v1 transpose, v2 transpose, vr. Okay. All right. So where am I going with this? Well, let's expand this out one last time. So the equation that we have is this. So the thing to keep in mind is that even though so far we do not know what the V's are, we can actually compute Y, right? Given a matrix X, I can just compute Y by computing X transpose X. And then I can raise it to a power L if I want to. Maybe I will do something more efficient later on, but at the very least, I can multiply matrices, so I can compute Y to the power L. But why is this useful in finding out what these V's can be? Right? Even if I can compute this, it doesn't tell me anything about how to decompose the sum of these matrices, or especially how to separate out the first one. Okay. To get some sense of what happens, let's take a particular example, a very simple toy example, right? So suppose just for normalization or for simplicity, let's assume that the first singular value, sigma 1, is actually 1, right? Then all of the rest, sigma 2 and so on, should be smaller than 1. And let's say they are kind of somewhat small. Maybe the first one is 1, and the second one is a little bit smaller than 1. As an example, let's say sigma 2 is 0.8, right? And maybe sigma 3 is something which is less than 0.8, and so on. Okay. So what does this tell us? In this case, Y to the L would have 1 times V1 transpose plus 0.8 to the power L times V2 transpose plus so on. Okay. As L goes to infinity, what is happening here? As I keep taking higher and higher powers, I'm not saying that's what we'll actually do, but let's say I do compute Y to the 10 and Y to the 100. So what happens to the matrix? If I compute Y to the 10, the first singular value, 1, stays as it is, and I have V1 transpose. But what's happening to the rest? So these are all decaying exponentially, right? So as I keep increasing L, 0.8 to the 10, 0.8 to the 20, 0.8 to the 100, these numbers will all start going to 0. So as L goes to infinity, as I keep on increasing L, the matrix Y to the L actually approaches V1 transpose, right? So as I keep increasing L, the matrix Y to the L actually approaches the outer product of the first right singular vector V1 with itself. So somehow it is doing some kind of filtering that we really wanted to do in the first place. If I keep taking higher and higher powers of Y, at least in this toy example, all of the remaining V2, V3, and so on disappear, and V1 is the only thing that starts dominating. Okay? So if I give you V1 transpose, how could you potentially get the first singular vector out of it? Remember, we are given Y to the L as a matrix. Right? So this is a matrix which has, what is the first column going to be? It is some multiple of V1. Maybe like so it's some scalar times V1, some scalar times V1, and so on. Right? So if we look at the first column of Y to the L and normalize it, then we should get the first right singular vector. So just take a high enough power of y to the L and look only at the first column. All of the columns are proportional to the, are almost proportional to the first right singular vector. So let's pick the first column. Okay. Then it's going to approach the first singular vector. All right. So this suggests the following algorithm. So let's make it into an idea. So we did this for a toy example, but kind of inspired by it, we're going to do the same, following. Compute y to the L for some large L, which is like 100. Okay. Compute the first column of y to the L. Okay. And I'm going to write down computing the first column as a matrix vector product. Hopefully you'll see y in a second. So this is my matrix y to the L, right? I want to extract only the first column out of this. One way to do it is to multiply this matrix with the vector which has 1 in the first entry and zeros everywhere else. Right? So let me call this vector E1. Some kind of, seemingly odd notation for the first column of the matrix y to L. I can extract the first column by just multiplying it with this vector E1, right? Let's call this V bar. And we want to output the normalized version of this vector. We know that the first right singular vector should have norm 1. So I'm just, whatever vector you compute, I'm going to normalize it so that it has length 1. Okay, any questions about this algorithm? Again, this is at a level of, kind of working for a toy example. And we'll see how to extend it or draw inspiration from it in a second. Okay. We're almost there, except power iteration has one other very important ingredient. It might seem like somewhat of a cheap trick, but it's very, very influential. And we'll see why in a few seconds. Okay. So what is the most important part of this computation so far? Right? Let's say this is the algorithm that we are zeroing on, and I have to implement it. What are we doing here? And what do you think will be the most expensive part of this 3 steps? Any guesses? I would say the most expensive part would be computing this matrix power y to the L. Right? So y can be a huge matrix. Right? So y is a big d by d matrix. Right? So y itself was x transpose x. Okay. And now I had to multiply it with itself d times. Sorry, L times. Right, so I have to compute this matrix multiplied with itself and itself L times. If L is 100, that's 100 matrix multiplications, right? So that's very expensive. But do I really need to do this? Is there, a better way to better way to do this computation? Any guesses? Well, look at what you really need for y to the L. So there's a very good suggestion here, which is to compute y raised to the power L over 2. That definitely helps. You can use that to save some matrix multiplications, but still, even a single matrix multiplication can be very expensive. Okay, my claim is that you can get around this issue and avoid matrix multiplications completely. You don't have to do any matrix multiplication. It's much easier to multiply a matrix with a vector rather than matrices with matrices. Okay, why could it be? What can I use? What is the magic bullet? Well, the magic bullet is that if you look at what we need, I don't need y to the L. What I need is y to the L times E1. Okay, I don't, in some sense, I don't really need to know what the entire matrix y to the L is, as long as I can compute y to the L times E1, or the first column. Okay. So what I need to be able to do is to compute, I have to multiply all of these matrices and then multiply with this vector. That's what I really need. Right? So doing 1 and 2 is computing y to the L and then doing y to the L times E1. But instead, if there's a way to compute this matrix vector product directly, that would be more helpful. Is there a better way to compute this? Instead of multiplying all of these matrices and then multiplying with the vector, what else can I do to speed up the computation? Any suggestions? Exactly, right? So you would multiply from right to left. Instead of multiplying all of these matrices and then multiplying with the vector, I can try and group things like this. Okay. So this way, I will never multiply a matrix with a matrix. I'll always multiply a matrix with a vector. Okay. Because when I multiply matrix with a vector, I get a vector. And then I have a matrix and a vector, I get a vector, and so on. Okay. So this is the final sort of, ingredient in power iteration, which makes it very scalable. Okay. So we are now ready to present our main algorithm, power iteration. So we start with a vector, V0. Now here we started with E1. Typically, so let's say I'm doing it with E1, right? And then I'll multiply the matrix with the vector that I just computed. Okay. And then keep repeating this for L times, and finally output the normalized version. So this is the power iteration. It's called power iteration because essentially you're computing the high power of a matrix times a vector, but you're computing this high power of a matrix times a vector iteratively. Instead of computing the power directly, I'm just going to multiply the matrix with a vector repeatedly. Okay, from right to left. Any questions about this? Okay, so this is for the so let's say first version. And the most general version, the one that actually gets used, is the following. All right. So let me state the full algorithm. So what does the power iteration do? Right. So its goal is to take as input a matrix, which is an n by d matrix. Okay. And think n is bigger than d typically. And our goal is a vector v that is close to the first right singular. We're not going to be able to compute the first singular vector exactly, but we'll be able to compute something which is very close to it. We'll even be able to quantify how close the vector is to it. Okay. So, I mean, the first version seems as good as it can get, but there's one, borderline annoying case which can torpedo the full algorithm, right? So what is that? What if y looks like this? So what if the first row and column of y are actually 0? Well, if I start with this matrix, what is y times e1 going to be? Well, y times e1 will just be all zeros. Right? And then my algorithm won't proceed. It'll just get stuck. It'll just say 0, 0, 0, and you'll get an awful answer. Even though y can still have a good singular vector, and singular value decomposition. Right? So here the problem comes from the fact that y could have some special structure for which multiplying with e1 can be a bad choice. Right? So what else can we do? Any suggestions? What could be a way to get around this? So to understand, how to get around this, let's go back to why we did this multiplication with E1, right? We said the matrix Y to the L, all of the columns are proportional to V1. They're just scalings of the first singular vector. And we picked the first column just because, it should still, we should be able to see it there. But even if the first column is 0, because the scalar multiple is 0, the second one should work, or maybe the third one should work, and so on. Right? So every column here is proportional to V1. So there's no specific reason to pick only the first column. We can pick any column, or we can pick any combination of the columns. Okay? So in general, when you're not sure which specific combination to take, it's a good idea to take a random combination. And this is exactly what the power iteration does. The final algorithm is the following. So I'm going to start with a random unit vector. Okay. And for t equals 1 through L, we want to compute this step, which is y times vt minus 1 bar. But remember, y itself was x transpose times x. Okay. And how should I do this computation now? Should I multiply x transpose with itself and then the vector, or do it from right to left? It's always better to do it from right to left. Multiplying a matrix with itself, is very, very expensive. Okay. So I'm going to do that thing exactly, right? So I'm going to say compute x transpose times x times vt minus 1 bar, right? And so in our first attempt, we said, okay, do this multiplication L times and finally normalize to be a unit vector. This works well in principle, but you try to do this on a computer, you will run into errors, especially floating point errors, right? So instead of multiplying like 2 to the 100 times and then dividing by 2 to the 100, you should normalize after every step, just so that your numbers don't shoot up very big and then you divide by very big numbers. Okay, so the actual algorithm that is implemented is the following. I'm going to first compute this vector ut, which is just in between, and then say vt bar is actually, say okay, instead of doing the multiplication L times and then normalizing the length, I'm going to normalize the length every time so that the numbers don't become very big in intermediate steps, and I'll lead to floating point errors. Okay, so this is the power iteration. Any questions about this? Okay, all right. So that's the algorithm. It's very simple, especially to implement, right? You're given your matrix X. All I need to do is the ability to compute matrix vector products. Given a matrix X, I need to be able to compute its matrix vector product. Okay. Does the result stay the same if we don't normalize in the end? Well, we definitely want a unit norm vector, right? Because the right singular vector must be normalized to have length 1. So you have to normalize at some point, and normalizing it in between is better because the numbers don't become very big. Okay, so if I multiply, instead of writing 2 to the 32 as 2 to the 32 divided by 2 to the 32, it's better to write it just as 1, because you might run into round off errors on when you're implementing it. Okay, so that's what you're trying to avoid here. All right. Okay. And is it X or Y? So here we really want to compute Y times VT minus 1 bar, right? But Y itself is X transpose X. Okay, so we really want to do it with a Y, but we don't want to compute X transpose X. It's a huge matrix. Multiplying 2 big matrices is bad. So I'm going to break it up again. So I'm using the same trick again and again. I never want to do matrix multiplication if I can avoid it. So I'm going to do matrix vector multiplication and another matrix vector multiplication. Okay. All right. So what can we say about power iteration? The good thing about power iteration is that it comes with some very precise quantitative guarantees. All right, so let me state them. Power iteration will converge to a top right singular vector. Okay. So in particular, so remember, V1 is the first principal component, right? So this means that x times V1 maximizes right? So which is and x times V1, its norm is sigma 1. Okay. So that means that to solve the first principal component, we had to solve this optimization problem. Right? We had to find a vector V which maximizes x times V divided by the length. And since V1 solves it, the best you can get is sigma 1. So what does power iteration do? How close does it get? Okay. So it turns out that after roughly t, which is O of log if I run the power iteration for something like log in the dimension divided by epsilon many iterations, then the vector Vt bar gives a reasonably good solution to the variance maximization problem. Okay. So if I run it for some log d or epsilon divided by epsilon iterations, it might not give me the first singular vector, but it is going to give me a vector Vt bar, which is reasonably close to the best one. Okay, and we can exactly quantify how close it is. As you run more iterations, it gets closer and closer. Okay, any questions about the statement? Okay. So in particular, in fact, you can say something even stronger. So let's say you have X, which is U sigma V transpose, right? Then let's say, remember we already said that we are writing the singular values in this decreasing order. So I have the first singular value, which is sigma 1. Maybe the second one is somewhat smaller, sigma 2. Sigma 3 is something a little smaller, and so on. right? Now, if the first one is 1, but the next one is 0.99, it's not clear which one you should call first and second. They're both very close, so maybe they're both within your margin of error, right? So we would like to fix some margin of error and say that maybe in this bandwidth of between 1 and 0.999, I don't really care if you gave me V1 or V2 because both are getting very close to the best possible, right? So we want to allow for some flexibility to capture this closeness, okay? So a way to do that is to look at this value, sigma 2, sigma 3, so on, and find the point where there is a sufficient gap between the first one and that particular one. Right, so if this is 1, this is 0.999, I don't really care that much. Maybe this is 0.98, it's okay. But at some point, it might become 0.8, and then I care about giving something, in this region. Can you hear me now?
Yes. Yes, we can hear you.
Okay. How much time did I lose?
I would say about a minute or 30 seconds.
Okay, that's not too bad. All right.
Yeah.
Yeah. Okay, I'm going to switch my mic to this one. Okay. So basically, let's find a point M where the singular value drops below the accuracy that we desire, right? Maybe if it's 1 and 0.9, I don't care. 0.91 also I don't care. But if it falls below 0.8, I don't want that particular vector, okay? And let's look at the span of the first, highest singular vectors. Right? Then the claim of so what we can show about power iteration is the following. We'll state the most general thing. We won't prove the most general thing, but we'll kind of try and understand why such a thing might be true by studying a special case. Okay. So after t iterations, where t is roughly some log 1 over delta by epsilon. So we cannot guarantee that the singular vector or the vector that is output by power iteration is very close to the first singular vector or the second singular vector. But we can say that it is very close to the span of the large singular vectors. Okay. So in particular, whatever VT you compute, it would be very close to being in the span of these top singular vectors. Right? And how close? The difference or the distance between VT bar and the projection onto SM, the error is small. That means delta. Okay. So that's what, that's the guarantee of power iteration that we have. All right. And we won't prove it. My original plan was to prove it, but we lost the lectures. I need to cut down some things. So we are not going to prove this theorem in its entirety, but it's just something to keep in mind that the convergence of power iteration is very good. Okay. Another way to think about this, again, just understand the statement of the theorem. Is that kind of an equivalent version after t iterations. You can actually prove something like this. Okay. So you start with some initial correlation. Okay, you start with some initial correlation, and as subsequent iterations go, the projection onto the other singular vectors keeps decaying exponentially. Right? So that's what this statement is saying. That as you perform more and more iterations, the correlation which is not in the span, the component of VT bar, which is not in the span, keeps decreasing exponentially. Okay. Any questions about the statement of the theorem? All right. So if there are no questions, then let me say some general remarks about power iteration and why it's quite nice. And then we'll just see some plots of what it can do. Okay. So the most important feature, I would say, of power iteration is the following. So let's look at this algorithm, right? So to implement this algorithm, what kind of access do you need to X. What is the least amount of access or ability, to manipulate X that you need? Any suggestions, guesses? Well, to make it more concrete, let's say I tell you, we need a little bit of access. So for example, let's say, I have matrices, let me give an example. So suppose I have these matrices x1, x2, x3, just for, imagine they are 100K times 100K each. Okay, I have 3 such matrices. I have these matrices stored, and I tell you, okay, can you compute the first singular vector of x times x1 times x2 times x3. Okay, so what would be one way to do this computation? You would say, okay, I'm going to first compute capital X by multiplying these 3 matrices together and run the power iteration on X. But is that what you would do? Is that the best way to run the power iteration? My claim is that there is something better you can do rather than multiplying the 3 matrices out and then running power iteration. Any suggestions on how I might be able to circumvent computing this matrix product? Well, we can use the same trick again, right? So remember, to do power iteration, what do we need? We need to be able to compute. So think of this as 2 steps. Well, okay, actually, let me just write it down. So I need to be able to compute X transpose times X times VT minus 1, right? Which is X1, X2, X3 transpose times X1, X2, X3 times VT minus 1. Okay. But once again, I don't have to compute this matrix product. I can do the multiplication from right to left, right? So the better way to do this multiplication is to say this is x3 transpose times x2 transpose times x1 transpose times x1 times x2 times x3 times this. Okay, but now I can group them like this. Okay, I can do the multiplication from right to left, right? So to run power iteration on X, I only need the ability to do matrix vector. Okay, I only need the ability to do matrix vector products with X. Okay, nothing else is really needed. Okay. In some sense here, computing the first singular vector of this capital X, which is a product of these three big matrices, might be even easier than computing X itself. It's a little bit counterintuitive, but it's basically saying that computing the first singular vector might be easier than even computing the entire matrix. Okay, easier computationally. Okay. And okay, so the other thing I want to say is we'll talk about how to compute the second singular vector, third singular vector, and other tricks in the next lecture. But I want to emphasize one other ingredient. Okay. So there is a way to actually view power iteration. Power iteration is, by definition, as we wrote it down here, a iterative algorithm, right? So you're doing one iteration after the other. You have some candidate V0 you started out with, and then we're kind of maybe refining it a little bit, and then refining it again, and so on, right? We saw one other iterative algorithm before, right? We saw several, but the main sort of meta algorithm that we saw before was gradient descent, right? And it turns out that power iteration can also be viewed as a version of gradient descent. In particular, it can be viewed as a kind of projected gradient descent. Okay. And if you can do gradient descent, then what's the next thing that you might wonder about trying? Well, anytime you can try and do gradient descent, you should try and think if I can use accelerated gradient descent to speed up the algorithm, right? And indeed, we can. There is a version called power iteration with momentum. Okay, and I'm not going to talk too much about it, but let me just write down what the algorithm is. So you start with the same intuition as before, which take, random unit vector, and for each, kind of time step, you try and update your algorithm, right? And the overall idea is to use the previous iterations to help your right? So, let me write it as X3, X transpose, right? So you have okay, so this is what we were doing before. In power iteration plus momentum, remember the intuition behind momentum is that you should use the past gradients or the past iterations to do some update, right? So you can do something like this. Okay, so that's kind of, adding the momentum term into the mix. Okay, and this is what power iteration with momentum looks like. Okay, you have to choose the beta parameter appropriately, but the idea is to incorporate what you learned already about the algorithm in this way. Okay.
Does it give any speed up? It indeed does. Power iteration has convergence roughly 1/epsilon. So where you go? Yeah, so see this epsilon here, this epsilon. To get epsilon close, I need roughly 1/epsilon iterations. Okay. And power iteration plus momentum, just like what we stated for accelerated gradient descent, power iteration plus momentum has quadratically better convergence. Okay, it's once again, momentum gives you a quadratic boost in how fast you run. Okay, so one thing to take away from this is the power of abstraction, right? So we saw gradient descent or something completely else. We saw power iteration. We presented it in a way that has nothing to do with gradient descent. But you can put at least heuristically put these two ideas together and then work out the math to make everything fit together. Okay. So let me do one thing, which is to show you a demo. Again, you should be able to see this on EdStem. Right, so here's code for power iteration. And what I'm doing here is that you can implement power iteration, and this is power iteration with momentum. There's just a beta term that it's kind of a free parameter that you have to play around with to make it work properly. And this is the default implementation that you see in NumPy. Okay, and I'm generating a reasonably big matrix, and so 1,000 by 100 matrix, and I'm going to run it for something like 1,000 steps, and I'm making sure that there is some gap between the first and second eigenvalues. So epsilon here determines how much gap I have between the first and second eigenvalues. Okay, so whether they're very close, like first and second singular values, 0.001 or 0.05 or 0.2. Right, as the gap increases, power iteration should run faster. Okay, and that is what we are seeing now. So you can see when the gap is only 0.001. So the gap between the first and the second, like, maybe the first is 1 and the second one is 0.999. The convergence to the first singular vector is somewhat slow. You need to run it many, many more steps to get close to the first singular vector, because the gap between the first and second is small, right? And this is on log scale. So you can see that it's actually decaying kind of at a log linear rate, which is what our theory also suggests. Now, Bond said that it should decay exponentially with each iteration. So when you plot the log of the error, it should be a line. Okay, and that's exactly what's happening here. And when the gap is slightly better, it's like 0.05, you see much faster convergence, the red line. And when the gap is even better, 0.2, you see almost like an instantaneous decrease in the gap error to the first singular vector. Okay, and the same thing, if you want to do it for momentum, you get the same sort of thing, right? And momentum, as you can see, kind of is even faster without momentum. Right? The black line is with momentum, and the green line is without momentum. The momentum step is much, much faster. Okay. And you can play around with this in the code. All right. So next lecture, when we come back, we'll look at some other implications or use cases of power iteration, and then move on to our next topic. Okay. All right. I'll see you all next Wednesday, hopefully in person, or if not, we'll figure out what to do. Okay. Bye, everybody.